Welcome back. In this lecture, we will derive a formula um, for the binding energy of a nuclear. Why is this called semi-empirical? Because this formula for binding energy of a nucleus will involve 5 constants, and this will be evaluated from some experimental data. Therefore, this is not a completely first principle model, but we'll use some empirical data to get these 5 constants. However, um, this has great validity because there are hundreds of nucleus, and we will not refit the data. With the same constants, it is possible to evaluate the mass and hence the binding energy of other nucleus. So it's a very, very powerful approach. It was derived by von Weizsäcker, and because binding energy and mass are equivalent, it is called a formula for mass. Let's move on. In an earlier lecture, we had seen the binding energy per nucleon is a constant, right? So this model, which we're going to be discussing, is applicable to nucleus which have A greater than, let's say, 30. Okay? So there is a steep rise in binding energy per nucleon, but after that, the binding energy remains more or less a constant. Okay, so based on that observation, we can say that the binding energy per nucleon is a constant. So B by atomic weight is a constant. Therefore, if you have to have a formula for the binding energy for the entire volume of the nucleus, that will scale to the first power of A. So let's say that constant is A subscript V, A sub V. So this is the formula for binding energy or the volume energy in a nucleus. So that also tells you something about the nature of strong nuclear forces. Supposing we have a model wherein each nucleon interacts with the rest of the nucleon. So for each nucleon, will interact then with A minus 1 nucleon in the nucleus. So there are A such interactions, right? Because there are A nucleons in the nucleus. So the total binding energy, because of this kind of interaction, that is each nucleon interacting with A minus 1 nucleons, should amount to A times A minus 1, which is approximately will scale as A squared. Okay. So if this is the model for strong nuclear forces, the interaction via strong nuclear forces, then B subscript V should scale quadratically. But this is an experimental observation. This suggests that B sub V scales linearly with A. So this kind of interaction, that is each nucleon interacting with um, all the rest of the nucleon, is not correct. So a better way of thinking about uh, strong nuclear interaction is that each nucleon interacts only with the adjacent nucleon. Okay, so in this manner, um, let's say the coordination number remains more or less constant. In this manner, we would see that each nucleon uh, interacting with just the nearest neighbor is a better model to get to the volume energy in a nucleus. So this is an important point, which also tells that the strong nuclear forces are very short-ranged. It decays. It does not. It's not felt beyond the nearest neighbors. So volume energy is also referred to as exchange energy. This sort of it is one and the same. It tells you some aspect of mechanism involved in strong nuclear forces, because it involves the exchange of force carrying particle. But if you see this term, this is one and the same as the volume energy in the nucleus. So we had imagined the nucleus to be a condensed nuclear matter. So if you have a condensed matter, um, let's say what you're most aware of is the solid and a liquid. So if you have a condensed matter, the condensed matter has a surface energy. This is in contrast to a gas, right? So if you have a gas, you don't talk about surface energy, because a gas is not a condensed matter. However, if you have a condensed matter, you have a surface energy, because um, we had motivated that many aspects of a nucleus is like that of a liquid drop. We can associate a surface energy with respect to nucleus. So the surface energy, considering a nucleus to be spherical, would go as 4 pi r squared. And in the previous lectures, we had given a formula for r, the radius of the nucleus goes as some radius constant times a to the 1/3, right? This is the atomic weight to 1/3. So putting these things together, we have a formula for the binding energy contribution to the surface, from the surface. So why is this negative? The way to think about this is the surface of the nucleus has lesser coordination number. If the coordination number is lesser with respect to the bulk coordination, the coordination is number, coordination is lesser. Therefore, with respect to bulk of the nucleus, the nucleons at the surface of the nucleus has lesser binding energy, right? So because of the lesser coordination, it interacts with lesser number of nucleons, therefore creating a surface of nuclear matter involves an energy penalty. Therefore, in contrast to the previous term, which is positive, um, this increases the binding energy, that is, makes it's a stabilizing number. When you say increasing, we are talking about increase in binding energy. So this is a stabilizing interaction. However, this is an energy penalty. Therefore, you have a negative sign. So this is a destabilizing interaction. Creating a surface is destabilizing in any condensed matter. So even in nuclear matter, it is a destabilizing interaction. Therefore, you have a negative sign here. So good homework to have for you to do is that you can first try to get a formula for fraction of nucleons in contact with the surface. Okay, so that's a good homework exercise. It involves some visualization. You can come up with a formula. So this answer to this is the answer. So typically, when you have a light nuclei, uh, most of the nucleons are at the surface. This is like what you see in a nanoparticle, right? So many of you might be aware of quantum size effect um, in the context of nanoscience. So in a nanoparticle, what makes it interesting is that the ratio of the atoms on the surface to the ratio of atoms in the bulk is a lot more, right? As the particles become larger and larger, this ratio decreases, and the effect of surface also is not that much, not that significant. Likewise, in a light nuclei, most of the nucleons are at the surface. There are very few nucleons in the bulk, right? So typically, this fraction is seen to be more than one. That is, the number of nucleons on the surface to the number of nucleons in the bulk. This ratio is greater than one. But as the um, as A increases, this this ratio becomes less than 1. The effect of surface is less. So even in all cases, we are going to be considering a spherical nucleus because our motivation is based on a liquid drop motivation for this model. And in a liquid drop, the surface tension and the surface energy of the liquid drop makes the liquid drop spherical. Likewise, we also assume that the nuclear matter has a spherical shape. So the next term to incorporate is the Coulomb energy term. So from classical electrostatics, it can be shown that if you have ZE, if that is the charge, this is the atomic number, right? So each nuclei has Z protons. And if these Z protons are uniformly distributed in a sphere, the electrostatic energy can be shown to be of this form. So using the formula for radius, which was mentioned in the previous slide and previous lectures, substituting that, you get to this form. And here, first thing you can try to do is derive this formula. Okay, this is just a matter of classical electrostatics. It's a good exercise for you to derive this formula. What you see here is as Z increases, the Coulomb repulsion energy goes in quadratically. It increases quadratically, right? So this is a destabilizing interaction because it involves Coulomb repulsion. It quadratically increases as with Z, and it is inversely goes as A to the 1/3. So this is the formula for the contribution of Coulomb repulsion to binding energy of the nucleus. Then there is something called asymmetry energy in the nucleus. This is because of the difference in the number of neutrons and number of protons in the nucleus. In light nuclei, the number of neutron is the same as number of protons. Okay, so we have seen this in a previous lecture. So, however, when you have heavier nuclei, the number of neutrons is much more than the number of protons. Why is that? We had qualitatively rationalized this feature in terms of Coulomb interaction, right? The Coulomb interaction goes quadratically as Z. As the Coulomb interaction increases, you need to have a lot more neutrons to screen each proton from each other. Not only that, having a lot more neutrons increases the interaction, strong nuclear forces increases. That's a stabilizing interaction. However, you should remember that the mass of neutron is much more than that of proton. So having a lot of neutrons is also destabilizing in some manner. So this formula is obtained from quantum mechanics. We are not going to derive the analytical formula. I mean, that is, we cannot argue qualitatively why it should scale as the square of this this difference. We are going to take it as accepted that this comes from certain quantum mechanical argument, which is beyond the scope of this course, and but we are going to use this expression. So again, this expression is a destabilizing interaction, and this interaction goes as difference between the number of neutrons to number of protons. So for light nucleus, this will not contribute to binding energy because N is equal to Z. So this is the expression for asymmetric energy. Then, to emphasize that this is a phenomenological model, we can also include some feature that is seen from experiments. We had seen in a previous lecture that uh, the most abundant nucleus have even nuclear configuration. That is, they have even number of neutrons and even number of protons. In addition, we had looked at the separation energy of the last nucleon, right? So that is, if you have a nucleus with even number of neutron, the energy to remove the highest energy neutron is lot more compared to the nucleus having an odd number of neutron. Likewise, if you have a nucleus that has even number of protons, the energy to remove the highest energy uh, proton is more compared to nucleus having an odd number of protons. So overall, it is beneficial for the nucleons to be paired up. That is, if you have neutron, it likes to be paired up with another neutron with a different spin. Likewise, if you have a proton, it likes to be paired up with another proton of different spin, right? So this feature can also be incorporated into our model for binding energy. Therefore, the binding energy increases if you have even nuclei. It is 0 for odd even or even odd nucleides. It is destabilizing if you have odd nucleides. So this constant we cannot derive by qualitative arguments, of course. It can be derived from some other more detailed model. It goes as a to the negative 1/2. So this, we assume that we can derive this from some other sources, but this feature will be incorporated into the binding energy model. So this is the fifth and final interaction. So just to recollect this, this term and this term, same, the expression for this term is given here. This is because of attractive binding energy interactions in the bulk, in the volume of the nucleus. This is the energy penalty due to the surface. This is the energy penalty due to Coulomb repulsion. This is the energy penalty due to asymmetry in the neutrons and protons. That is, if you have more number of neutrons, that introduces a destabilizing factor that is incorporated here. The order uh, odd, odd even, or even nuclear configuration also contribute to binding energy. So all the 5 terms have been assembled. So what is the next step? So the next step is, take this formula. We have the mass of 5 nucleus, right? Take any 5 appropriate nucleus, heavy nucleus, wherein this model is valid. These masses can be found out accurately from mass spectroscopy. Once you have the masses, we also have the binding energies, right? Because the mass, because of Einstein's E is equal to mc squared, because of that relationship, when we measure mass, we are measuring binding energies. So to obtain 5 unknowns, that is AV, A sub S, A sub C, A sub A, and A sub B are unknowns, we use the mass and binding energy data from 5 different nucleus, and we can get these constants. Once you have these constants, what can be done? What we can do is that this is a very powerful formula, right? So once you have the constant, uh, this constant suggests that B is just function of A and Z, right? for any atomic number and for the relevant atomic weight, we have a general formula for binding energy. So this is a very powerful result, right? So this can be utilized for getting the mass of any particular nucleus, right? Because the mass of proton is known, the mass of neutron is also known. This B can be obtained from this formula. Therefore, the mass of any unknown nucleus of atomic number Z and atomic weight A can be obtained using this semi-empirical mass formula developed by von Weizsäcker. So this is an important model that is utilized in nuclear science. So it's important you understand that. So this is not the only application. This has a lot of consequences. We will look at some of the consequences starting in the next lecture. We will look at some of the applications of this formula. Thank you.